So welcome to the fifth lecture of MCS 471. So the fifth lecture on root finding with Newton's method. So as you can see, the lecture has two parts. So first we will derive the method, and we will see how to define the method in Julia. And we will define a Julia function, and the setup for this Julia function will be done with symbolic computation package, SymPy. So in the first part, we derive Newton's method and we define the function that will allow us to do computational experiments. So in the second part, we define the convergence of Newton's method. In particular, we will see that Newton's method is a very great method as it converges quadratically. So first we have to make the distinction between linear and quadratic convergence. And we will end this lecture by indicating what happens when our equation has multiple roots. So we have seen in the last lecture that multiple roots were causing problems for numerical methods. We will actually see that Newton's method no longer converges quadratically when approaching a multiple root, but that Newton's method then converges geometrically. All right, let's dive in. So Newton's method you must have seen in calculus as an application of Taylor series. So what happens is that we are starting from an initial approximation, so x naught, and we want to compute a correction, delta x, so that at that correction, when we add the correction to the initial root, we actually do have an equation. So to solve one equation, we will solve another. But now actually, we will assume that the delta x is small, so we can throw away the higher order coefficients. So often we have already two decimal places of our initial approximation, so the error will be 10 to the power minus 2. Then if you square that, the delta, the second order term, is 10 to the power minus 4. So 10 to the power minus 4 is a lot less than 10 to the power minus 2. So we ignore it. So in the Taylor series, we are then left with one equation for which we observe that optimistically we want actually that when we add the correction term, we have a 0. So our equation actually then furthermore simplifies, and then we can quickly solve for delta x. So dividing by the derivative at the initial approximation, that will give us the update that we'll be using to correct the initial approximation. So this gives us a formula that we can repeat. So in the next step, we replace x naught by x1, and applying the same formula, we get x2. That's one derivation. Suppose we forget this, then we can think geometrically. So we want to compute a root, so we have a blue f, and actually this blue f is a parabola. It intersects at 0 and at 1.5. So it has two roots here. So we are actually here quite far at 3. And at 3, we evaluate and replace the blue f by the tangent line. So the f is a quadratic. They're actually very easy to compute the roots of, but let's ignore that for a minute. Linear equations are actually easier to solve. So we solve for the equation for the line. So that means geometrically, we look where the tangent line hits the horizontal axis, and that will be our next point, x1. And we continue doing that. So at x1, we do the evaluation, and then we compute the tangent line, which I try to draw here, and the tangent line will give us the next approximation, x2. This gives us the geometric origin for Newton's method. And we can formalize this and derive a formula. So suppose that we forgot Taylor series, but we know the equation of a tangent line. So the equation of a tangent line involves the derivative. So remember, rise over run. If you write this out, then you will find here this equation, which is solved when we compute the intersection of the tangent line with the horizontal axis. So doing some algebraic manipulation actually gives us the next point. You see we have the correction term, what we subtract from the initial approximation. So the main result is a formula. It's an iterative formula, so it goes on for however long we want it to go on. It's also the formula, it takes the shape of a fixed point iteration that we discussed in lecture 3. So we have a formula, we don't yet have a program, we actually also don't have an algorithm yet. So we will now define this method into a function, a Julia function. Just recapping, so we have Newton's method here applied to an example. So we have a cubic polynomial. In some sense, this is the running example through the first part in this lecture. So a nice polynomial, degree 3, its derivative, and then we can also spell out the iterative formula. Typically, we won't be doing this, but here this is done to kind of resolve the mystery of that third lecture, where we derived a fixed point iteration from the original equation. And how this was done was actually kind of magical, was left open. Especially the last example there was kind of contrived. It worked out well. We had a very fast fixed point iteration, but it was kind of mysterious how we got it. So in a way, we could see Newton's method as a method to make fixed point iterations. So the formula that is on this slide here is the same formula as we used in lecture 3. All right, all good on paper. So let's now go to the definition. So we want a general implementation that will work for any expression in one variable. And what we can do for that, so our Julia function will take functions on input, but to make the input, we actually will start from strings. So our program will prompt the user for a string, which is the string representation of any general expression. Well, here on this slide, which is a interactive session at the Julia prompt, we have installed the Julia package, and we declare the symbol x. X has a string representation x. We have the object x, which will be used in the SymPy expression. So SymPy takes any string and it parses the string, it converts the string within the symbolic context. So if that string contains the symbol x, contains the letter x essentially, then that letter x will be replaced by the symbol. So here you see that x to the power 3, what you represent as a string here, is here interpreted in the pretty printing as x raised to 3. SymPy is very useful here. The other important construction is the lambdafy. So lambdafy takes any valid SymPy expression and turns it into a Julia function. So we can evaluate a SymPy expression by substitution, and we did this in last lecture. But here we don't really want this. We want a function that is no longer requires us to know the symbol. So here you can see at the bottom of the slide, I can just use this function evaluated at a number. So we evaluate this at the integer. These are the key ingredients. Let's now formalize this in another function. So functions are good to encapsulate instructions that we are confident about. So we will prompt the user for a string, and we have to compute the derivative. We don't want to prompt the user also for the derivative. For that purpose, we use SymPy. So these instructions on this slide here define a self-contained Julia function using the SymPy package. In the context of the function, x is a global variable in which we will evaluate the string passed as input argument to the function. So we execute the SymPy and we get a valid SymPy expression that we can differentiate. So here you see the critical operation. Here we get the derivative of our expression given as a string, the expression which is symbolic, which is in the symbolic variable x. So we then leave SymPy returning the string representation of the derivative. So that's our first helper function. The second helper function will encapsulate the SymPy derivative to compute the update. So we have an iterative formula, and in that iterative formula, we always correct the current approximation by adding what is here called the delta x. So we could define Newton's method as this right-hand side of the fixed point iteration. So we could essentially have defined the function g of x, which we used in lecture 3, but for numerical reasons, we are not going to do this. We want a numerical function in which we can estimate, in which we have an estimate for the error. So the delta x here is a function, but the value, what we add to the current root, is also an estimate for the forward error. So if we, in particular, if we have a converging function, we hope that delta x becomes smaller and smaller. So that's why we will actually have a function that computes that update. And here you see how this is done. So we are having on input, and actually I should say with Julia functions, what is very useful is having extra arguments. So if you are developing a function, sometimes it's good to print some test messages. So here I want to see what is the symbolic form, what is the string representation of my update. So here I'm doing a string concatenation in the second statement, and I want to see what is the string. Make sure that I haven't forgotten any brackets. So I'm concatenating this string here to that string, to this string, to that string, to this string. So I have 5 strings that are concatenated together. So I will have the string of representation for the update that will be simplified and lambdified. So what is returned here is a function. And what is on the slide is then our second Julia program that is posted. And that actually shows, for this particular, for our running example, this shows the expression as a string and also shows that you can use this as a Julia function. So this is the second encapsulation of SymPy within the global variable X context. All right then, so here I can now define the Julia function, starting with the entire documentation string. So there are 3 input parameters: the function, the update function, and the initial approximation. These are the first 3 parameters, 2 functions and 1 64-bit float, which the user must provide. The next 3 arguments are provided with default values. And default values are very useful to give the user kind of an easy way default setting. So in particular, we will not allow any more than 6 steps. That is taking into account the fast convergence. If later in this lecture we go to multiple routes, you will have to change that default. So 6 will no longer suffice if we are converging to a multiple route. The tolerances, so now we have 2 tolerances. So when we defined fixed point iterations, we were kind of sloppy and working with 1 tolerance. But it's good to actually have a tolerance on the forward error and a tolerance on the backward error. Or what is here explained, so the backward error is the residual. And also as we have the magnitude of the update. So if we have a converging method, that what the correction term will get smaller and smaller. And if it drops below 10 to the power minus 8, we stop. We will also stop when our function value is below 10 to the power minus 8. So these are both sensible defaults when we run with 64-bit floats. All right, what is returned is a tuple. We not only want the root, but we also want the estimates for the forward error and the backward error. So here you see the forward error, the magnitude of the correction term, and then the magnitude of the residual is actually the estimate for the backward error. Numerical methods may fail if the tolerances are not met. Then the boolean, the last boolean in that tuple will be true. All right, this is the specification. It's a lot longer, or just at least as long as the definition. So the definition of the function actually consists of 4 lines. So we have this for loop here. We evaluate the function at the current approximation of the root. We also evaluate the update. Here I take already the absolute value, and I'm forcing here the 64-bit representation. So in some sense, the 64-bit arithmetic is already enforced because the X naught is already a 64-bit, but just to make sure. So that's the main part in this function. This was essentially the formula. The formula translated into code with the for loop. Then we have the stop criterion. So here you see the tests on the correction term and the test on the residual. And this vertical symbol here is the OR. So if one of the stop criteria are met, then we stop. We return false as the last element in our tuple. We have succeeded. Otherwise, if we run out the loop, then it meant that we have exhausted our maximum number of iterations, and both stop criteria were always failing, both of them. So that means we have failure. So the stop criterion is the other important ingredient in the definition. The last, the third ingredient in the definition of the function are the formats of the output. So the roots we write with full precision, 16 decimal places, still in scientific format. All the floating point numbers are written by default in scientific notation, so that's what this E means. But for the errors, we do actually mainly look at the exponents. So there, the fraction should be written with a lot lesser accuracy. So the step numbers are printed with a fixed number of decimal places. That's to have a nice layout in the table of steps. All right. Then we have the main function, which looks rather messy, but we'll just say that the main function consists of the following instructions. Actually, we have only about 3 instructions that matter, 3 lines that matter. So we have the definition of the function f that comes from a string, is simplified and lambdafied. F is then a proper Julia function. And then we have the construction of the Newton update that also gives us the another Julia function. What comes before the block that I encircled here are the parsing, the prompting and the parsing. What comes afterwards is the printing. To do this within the proper context of a main function. So this is terminal window programming. I will try to go to the Jupyter notebook after showing the output. So this is a screenshot at a terminal window where you type in Julia and the name of the Julia program. That will prompt the user. So what the user types in is this cubic polynomial and the initial value. And then you see the confirmation of the update operator. So the default verbose is true. And then you see the running. So after 5 steps, we have a very accurate route. So you can actually also see this when you compare the decimal places in 2 consecutive approximations. So here this says that we have at least 7 decimal places. So already after step 4. But we go 1 step farther because of the 10 to the power minus 8. Observe the very fast convergence. So we go from an order 10 to the power minus 4 to 10 to the power minus 10 to the power minus 2 to 10 to the power minus 4, 10 to the power minus 3 to 10 to the power minus 6 in the residuals here. So very fast. So we will see this as a sign of quadratic convergence. All right, before going now to the next step, I will switch to the Jupyter notebook So I will share the screen here. So the definition was done within a conventional terminal window. Now the setup is done within the Jupyter notebook. So the Jupyter notebook we use to document our computations. So in some sense, it is a more comprehensive environment that provides us with graphics. So there are coding cells, and there are what you see here markdown cells. So the Newton's method that is highlighted here is a markdown cell, and then there are code cells, and then there are output cells. Right, so here you see the recap for the geometric derivation again. So the markdown cells contain LaTeX code. So what I want to point out is that not only the plotting, but also the definition of the functions. So one can copy an entire Julia program in one cell, but please don't do this. Every cell that contains code is one logical action. So in code cell 6 here, I'm indicating that I will be using SymPy. X will be the symbol that will be used to denote the independent variable. In cell 7, I am defining the function. I'm copying and pasting the definition of the function. And when I'm executing this cell, I will not execute anything here. When it gets executed, the cell that gets executed results in executable code. So in cell 8, then that code is executed. So what is important here when you use the Jupyter notebook is actually when you copy code from a Julia program into a notebook interface, you actually do no longer have a main program. If you're using a graphical user interface, you do this with pointing and clicking. You as user are actually the driver. You no longer prompt it. Instead of a prompt, we actually provided a string in this function SymPy derivative here. Instead of a print statement, we actually see the output. So that is important. So this Jupyter notebook executes as one program. So when you load in this Jupyter notebook, you have to run it. So essentially, you can do this when you go to cell, you can run all. So I will not do this, but this was actually executed one instruction, one cell block after the other. So when you design your own notebook, when you give the answers to the exercises or to a computer project, you also design the functions so that everything runs consistently. So there is actually a little bit more thought that has to go into a good, a well-designed Jupyter notebook. But the result is very nice. So here you see the second function where the Newton update, the update to Newton is defined. Again, there's no main program. Here you see the simple test that allows us to verify the correctness of this function. And then and only then do we have actually the main function that is used to run Newton's method. So we are formatting our numbers in scientific notation. So this is where we use the printf. And we copy and paste into this code cell the definition of the function. Just as was on the slides. And here you now see at the very end, actually the punchline of this scrolling through is that instead of, we had on the slide, a very dense slide with the main function, there is no main function here. We just have 4 lines. We define the string representation of our cubic polynomial, the running example. We define the function, so actually I'm skipping instructions a little bit. So fx was actually the second instruction, where we are here, as my cursor is hovering around it, we are defining the Julia function, applying the SymPy and the lambdify, and then we apply the Newton's method. So this gives us then the first 2 parameters, the first 2 functions for Newton. And you see the same running that was done here. All right, so that's the end of this demonstration. I will go back to the slides and go back to the point where we left off. So we left off with this running, which is in a terminal window. In a Jupyter notebook, this appears in an output cell. All right, we are midway. Time for some exercises. So the first exercise starts by asking to explore the sensitivity of the start value. The root was kind of 0.6, and we started at 0.5. What if we would, instead of 0.5, we would start at 0.25? How fast will it then still converge? Or what if we start at minus 0.5? We will still converge then. Or minus 2. So on the real axis, what if we would go further and further to the left of this? So that's one experiment. Now, that experiment can go on as much as you like, but do sufficiently many experiments so that you can answer the question. There is actually only one real root. So the question is, will Newton still converge, even if you are very, very far away from the actual root? Experiment. The second question is, what if you get much closer? So you get closer, so you can actually take 0.6, but you can also overshoot it. So you can start at 1 now. You can start at 1.5. And actually, you can make this as far as you like to get actually the second problem that we observed in the last lecture. You can get very, very large numbers. The x to the power 3 may get quite large if it gets to 1,000. So exercise 1 asks you to see if you can break Newton's method on this running example. The second exercise asks you to compute the complex roots. So unless you do complex arithmetic, you will never reach the complex roots. So the second exercise, you can modify the function. So the input type is float 64. You can wipe that out so that you can also provide complex numbers. Or you can use the Newton updates. And so it's not necessary to answer this exercise that you provide a completely new function. That's of course nice, but you can just indicate how you can use Julia as a calculator, running Newton's method now with complex arithmetic. You can define functions that actually return complex numbers. We've seen how to force the 64-bit float arithmetic, You can also force the complex arithmetic. You can complexify the polynomial as well, adding somewhere a complex, a very, very tiny complex number to it, very close to machine precision. That's another trick, how you can trick things. So Newton's method, so the result of this exercise is that Newton's method also works with complex arithmetic. All right. Now we get to the second part of the lecture. How can we define the convergence? Newton's method converges fast. We will say that it converges quadratically. So first we have to define what we mean by that. Going back to the bisection method, we get one bit in every step. And since the two logarithm of 10 is about 3, a little bit more than 3, we get about 3 to 4 steps to get one more decimal place correct. What we actually observe is that when we compare two consecutive errors, so here this notation means that we subtract from the exact root the current approximation and we take the absolute value. We take the ratios, and that should be about a constant. Of course, this is a mathematical definition, and it's only valid if we have a converging sequence. Otherwise, the E sub k goes wildly diverging as well if we don't have a converging. And also, it will only be valid in the limit if we are actually already sufficiently close. And that same positive constant will kind of fluctuate, like with the bisection method, will be around 3 point something, between 3 and 4. Quadratic convergence is very similar, except now you see here that I have indicated this, highlighted also in red, that the next error is one magnitude smaller. So we go from 10 to the power minus 2 to 10 to the power minus 4, from 10 to the power minus 3 to 10 to the power minus 6. Now, again, this is approximately. Sometimes you go from 10 to the power 3 to 10 to the power minus 5, or from 10 to the power minus 5 to 10 to the power minus 9. So it's not exactly, so it's approximately. But you see that there is a, approximately, we say that in every step, Newton's method or any quadratically converging iteration will double the correct decimal places in every step. So, and you can observe this if you look at the exponents in the error. And you can compute this also here by computing the ratio of two consecutive errors. All right. This slide here turns back to fixed point iterations. So here you see the formula for the fixed iteration. We observed in lecture 3, at the end of lecture 3, extremely fast convergence. And geometrically, we then said this was because the fixed point iteration function, the g, was very flat. Actually, the derivative, the tangent line there, was horizontal. Now we can generalize this. Not only the tangent line, but also the second derivative can vanish. So not only the slope, but also the second derivative, the curvature is 0, etc., etc. So we actually can define the order R by saying that first R minus 1 derivatives of the fixed point iteration equals 0. And we can apply this to Newton's methods and observe that at the fixed point, we actually have that derivative is actually 0. provided, and here there is a big if statement here, that the derivative at the root is different from 0. Otherwise, we can't do this. So Newton's method converges quadratically. Here, actually, you can verify this with this definition. So the derivatives are done symbolically, but we can already run SymPy. So actually, you can verify this expression, let a computer do this. So you can see at the fixed point, this term here disappears. And you see you have 1 minus 1 because the numerator equals the denominator. So in some sense, this is a formal proof that if the derivative, if the root is not multiple, then actually Newton's method converges quadratically, or at least quadratically. You can have also methods with cubic convergence, but then you must use the information from the second derivative. All right. Here is another exercise, another application, if you like, of Newton's method. If you don't have a square root function, or if you have to define your own square root function in an arithmetic that is not provided, then Newton's method will converge very fast. And a standard start is actually the x naught equals 7. So when we derived Newton's method, I said that you can look at Newton's method as a method to set up a fixed point formula. So to convert the root finding problem to a fixed point finding problem. And that is actually what this exercise does here. So exercise 3 is just a symbolic exercise. So for which you will already give half of the credit. So there are a lot of exercises in this class, but many exercises are often just verifying things. For the second exercise, you have to draw a cobweb diagram. As it is written here, you can attempt this on paper, but please don't do this. Please use the posted Jupyter notebook for lecture 3. So drawing cobweb diagrams can be very delicate. Well, delicate in the sense that if you care about the correctness. So as soon as you have the slope of the fixed point iteration wrong, your iterative method will actually behave differently. So these diagrams are very sensitive to the accuracy of the plots. So in some sense, this exercise is combining lecture 3 with this lecture for a specific application for square root. So you will see that if in a couple of iterations you can compute square roots quite accurately. All right, so now we get into the last 10 minutes of this lecture. What happens when you have multiple roots? Well, first of all, what is a multiple root? Well, in a multiple root, you have that the first m derivatives are m minus 1 derivatives are actually vanishing. So double root is when the first derivative is 0. Triple root, also the second derivative is 0. And this goes all the way up. What does this say about the Taylor series? Well, at the Taylor series, we have that actually they start also with the mth derivative of the function, which we will abbreviate by the constant c, and we will also ignore higher order terms. So the function actually then behaves like x minus r to some power m, where m is the multiplicity. We can also say this about the first derivative and the second derivative. So what good does this do? Well, we are interested in the question, what happens to the convergence of Newton's method if we are actually converging to a multiple root. And here I should point out that our implementation, our definition of Newton's method was actually kind of implicitly assuming that the update would always be valid if the derivative would not be zero. So a more robust implementation, or in a way, we shouldn't really worry that much about this because we are working in a robust environment that supports exception handling. But to be a little bit more careful with our coding, which we will not pursue here, we actually should have had some kind of guard on the magnitude of our derivatives. We don't want to divide by zero. Okay. What happens to the order of convergence? So we defined the order of convergence by saying that we had quadratic convergence if the derivative, so if the derivative of our fixed point iteration vanished. So here we have it again. So actually the slide starts with this formula. So if we have quadratic convergence, so f of x is 0 at the root, then this at the root, the derivative is 0. So we have this with a regular root. But now actually we can't really say, so the denominator here at the multiple root becomes 0. So, and actually we have then 0 divided by 0. And we can't really say that this is 1. Okay, how can we get out of this? Well, we replace the expressions for f by the leading terms in this Taylor series. So here we have the Taylor series expansion. We plug that in. And we see that everything simplifies. So the expression which we will not evaluate at the root, so actually I should actually have used here also the wiggle symbol. So this is not exact. So in a way, this is an approximation. So it turns out that, and this expression is only valid if x is sufficiently close to r. So these Taylor series are valid when the higher order terms are sufficiently small, and this happened when x minus r was sufficiently small. All right, we get to the main result, the m minus 1 divided by m. So it's not 0, but it's also not larger than 1. So we've seen that in the iterations, in the fixed point iterations that diverged, the repelling fixed points, that there we had that the derivative was larger than 1. So the slope started to be rather steep. Okay, so we just proved this theorem. I should also have pointed out that another interpretation for the derivative. So here I have the derivative at the root was actually the bound between two consecutive errors. So I had the error at the kth step, and that was actually the multiplied with the derivative. So what I'm writing now was actually a reformulation of why this derivative of the fixed point iteration at the root was actually so important. So knowing proofs of theorems is very useful. So we actually did, this is not a proof-driven course, but it's somehow important that just before we get to the punchline of the statement of a theorem, we have actually derived a nice expression. So we also derived the rate of convergence as the rate of two consecutive errors. So this is where this m minus 1 over m comes in. The next exercise exercise is saying that you can fix Newton's method. Fixing means you can restore the quadratic convergence if you know the multiplicity. So you're going to redo the calculation on the previous slide. So the previous slide here, let me scroll back, you derive this for this particular fixed point iteration for G. So now you have a modified G. So this is, if you like, don't call it G prime, call it H. And now you compute H prime. Also using now the same Taylor series expansion. And you will see that there, the rate of convergence, so when you compute that derivatives, you will actually have 0. In the limit, you will actually have quadratic convergence. You can by hand, but SymPy is extremely useful here. So you can do everything with SymPy. All right, last exercise. So we are at the end. So the higher the multiplicity, the closer the rate of convergency comes to 1. So multiplicity 2, your rate of convergence is 1/2. Multiplicity 3, your rate of convergence is theoretically 2/3. Now, do you observe that convergence rate? So here you have to run Newton's method again. You could do it modifying the function, having a step, having an extra print statement getting in there. So where you actually compute the rate of 2 errors. So here actually in this particular example, you know the exact root 1. And you always compute the difference of your current approximation to 1. But you can also use the delta x or the residual in the Newton's method. So if you converge, they are all about the same. You can use the posted function, but you can also actually make your own Newton. So you have the update and you have the function, and you do 1 Newton step. And you compute as you would with the hand calculator. Then the last part of this exercise asks you to modify the Newton's method with the multiplicity on this particular example. And the question now is, does your modification converge quadratically? You could do this by modifying the posted Newton, by having an extra argument, your proposed multiplicity. And what you do is you multiply your correction term with this proposed multiplicity. But for this particular exercise 5, you could also do this by so-called by hand, doing this step by step. So in a sequence of Jupyter cells, you compute more and more. Or if you're a little bit more into thinking programmer-wise, you have a for loop that you execute inside a Jupyter cell. Okay, I have to stop here. So this is the end of the lecture.